One of the questions that I get asked a lot in my work is, how does climate change affect my work? And I think in order to answer this question, it's really helpful to pull back and look at it in some context. So in 2024, Hurricane Helene hit the east coast of the United States, particularly North Carolina. It did about $60 billion in damage, and there were at least 250 people who died. If we look at this in the context of billion-dollar disasters across the US, this is anything adjusted for inflation that exceeds $1 billion in impacts. Hurricane Helene was one of 27 events in 2024. And if we zoom even further out, since we started tracking this data in 1980, we can see that there's been a sharp increase in the number of disasters. If we break it down by type, I've highlighted in yellow everything that's a severe storm or a flood. So the vast majority of these disasters are made up of those. The others might be droughts, wildfires, winter storms, there we go, and others. And in order to do this, we need to understand this concept of stationarity. So the Army Corps defines stationarity as it means the statistical properties of hydrologic variables in future time periods will be similar to past time periods. I think of it a little more simply as stationarity means things don't change with time. So let's look at an example. What if I told you there was a thing that between 1984 and 2024 never changed in value between 1.5 and 1.65? So everything would fall within this 100% confidence interval. I'm very obviously talking about the price of a Costco hot dog, which has not changed since its introduction in 1984. But I think this is a really good example of a stationary product. Time went on, but the only little variations are local sales taxes. So what about rainfall? What I've graphed here is the 24-hour rainfall depths in the district since we started tracking in 1985. And from a stationary perspective, you could look at this and say, because the past can predict the future, this is kind of our band where we think things are going to happen between. And we can use that to help predict what might happen in the future. If we go on in time and suddenly a point falls outside of that, that's actually not a problem with this assumption. We just didn't have enough data, and we can change our range. But the question becomes, as more and more points fall outside of that range, and this assumption of stationarity gets challenged, what do we do? So if before we were thinking about stationarity, now we need to understand non-stationarity. So again, I showed you the Costco hot dog, $1.50 to $1.65, depending on your state. That's a stationary thing. It didn't change with time. A non-stationary example might be the price of a hot dog at any baseball stadium, which has steadily gone up in price since 1984. It used to be about $1.50, and if you're at Coors Field now, I think a Rocky Dog runs you like $8. So if everything's always changing, how do we plan? There's this concept called a shared socioeconomic pathway. The simplest term is it's a narrative that we can use to describe what a possible future might look like. There's 5. They come to us from the International Panel on Climate Change. And today we're going to focus on just 2 of them. So first off, we have Pathway 5, which is taking the highway. This represents a future with heavy development, a high energy demand, and critically, most of that energy is found through fossil fuels. I've graphed on the y-axis there, it's the carbon in the atmosphere. On the flip side, we have Pathway 1, which is taking the green road. This represents green infrastructure with the majority of our energy needs being supplied through clean energy. These are really helpful planning tools to help us anticipate what a future might look like, even if we don't exactly know what's going to happen. So last year at this event, I presented to you on climate change impacts, kind of the basics of it, and I talked about some of the work that we were doing. And I'm really happy to share some of the progress that we've made since then. I think the easiest way to do this is to break it down into 3 segments. So past, present, and future. Starting in about 1985, we started collecting rain gauge data across the district. Today, we have about 244 gauges, which we then supplement with external daily gauges. Then, we worked with Applied Weather Associates, Bill Capel, and Dr. Doug Holtstrand to create gridded precipitation data for the district area, similar to a product that you might see like Atlas 14. And then the fun bit, at least fun for me, for nerds. We did the modeling. I'm showing you this graph here right now, but I need you to promise me that you're not going to try and read it. We're going to break this up into 3 segments. So the first thing that we did is we used the NASA Earth Exchange Global Daily Downscale Projections, which is a mouthful, and I had to practice a bunch just to make sure I could do it here. But really, that's just an ensemble of climate models that we can use. Then we take our data, we put it into the models, and we do what's called hindcasting, where you make sure that the models are able to tell you what did happen accurately. Once they're calibrated, you then project into the future and can get results on what these future scenarios might look like, all based on the pathways that we talked about earlier. So that's what we did. I'm really excited to share some of the results with you. Everything I'm about to show you is based on this Pathway 5 scenario. So first things first, temperatures. Compared to the historic average, which I have there in yellow, in the winter, we're projecting, in the worst-case scenario, about a 35% increase in temperatures. And that might mean that we have a decreased snowpack. In the spring, we're looking at about just over 20%, which might mean that we have an earlier growing season. In the summer, we're looking at about 20%, which might mean that we have more intense heat waves. And then finally, in the fall, we're looking at just under 30%, which might mean an extended wildfire season. Okay, so that's temperature. When we look at precipitation, and again, we're going to compare it to the historic average, which is in yellow there, year by year, we're projecting about a 20% increase in yearly precipitation on 30-year average. And I think that's interesting, but I think even more interesting is when we break this down by seasons. So, winter, we're looking to see a pretty significant increase in precipitation. That might mean we have a higher chance of rain on snow events. In the spring, we're also looking to see potentially wetter growing seasons. But the fall and the summer look to be, pretty close to average. Summer doesn't change much. Fall has a, maybe a 7% increase. Let's dive into that a little more, because I think there's a lot of interesting data there. And specifically, we're going to look at the summer here, because I have only so much time and only so many graphs that you'll sit through. So instead of percent increase, what we're looking at now is the average monthly rainfall in the summer. So like any given July, you might be able to assume there's about 2 inches of rain on average. And here's the thing about averages. On average, between me and Tom Brady, we've thrown for 44,607 yards, 325.5 touchdowns, and 3.5 Super Bowls. You guys have no idea how happy that you laughed. So averages don't always tell the full story. Instead of looking at the historic average, let's look at the confidence interval. I showed you this earlier, actually, with the hot dogs. This was our confidence range where all of the data fell within. Every single Costco hot dog fell within this range. That's what we're going to look at here in a second. So, compared to the historic 95% confidence range, our projections are showing increases on both the high and the low side for the summer. This all represents new additional risk. On the high end, it might mean that we have more probability of more intense and more rainfall, but also more probability of droughts, more variability in there. So for the fun bit, what does it mean? I'm pulling back up the temperature slide that we looked at earlier, and I'm going to put it side by side with the precipitation, because I think when you look at these in tandem, there's a couple of interesting things that might be a takeaway. So what if we had a wetter growing season that was earlier with a decreased snowpack? Does that mean we might see more spring vegetation? What if we had a higher chance of rain on snow and a wetter growing season? Does our flood season move up? Okay, what if a decreased snowpack and more extreme heat happened? Are we going to face water scarcity issues? And then, if I bring in that variability chart from before, and again, this is just for the summer, And if we thought that there was an increased drought potential, along with more extreme heat and a longer wildfire season, maybe we see more extreme wildfires. If you know me, you know I have a billion thoughts on this, and I will talk your ear off about what this might mean, but I'm actually more interested in your thoughts. So if there's anything here that sparked your brain, that you want to talk about, reach out, questions, please email me. I really do want to hear about it. So the big question, what do we do? In 1965, Hurricane Betsy hit the coast of New Orleans. There was about $1.4 billion in damages, and at least 5 people died. As a result of that, the US passed the Flood Control Act of 1965, which authorized new levees in the area, and importantly, it approved major infrastructure along the Mississippi River. So, we had a challenge, and we responded. Okay, we want to build all this new infrastructure, but cross-sections are really hard, water surface profiles are really hard to do by hand for regular cross-sections. Okay, we have a challenge. Well, then the Army Corps releases HEC 2, which allowed for the processing of these water surface profiles from the personal computer. Challenge, response. But let's think about HEC 2 for a second. What would you do if somebody submitted a HEC 2 model to you today? This was a revolutionary product when it came out, and it fundamentally changed the way that we work. But today it would be out of place, because we have new problems for our new age. So at the beginning, I asked you the question of how do we respond to climate change in our work? The challenges that we face, they're here now. They're not tomorrow, they're today. The only certainty that we have is that the future is going to be different than it is now. But we can't flinch in the face of this uncertainty. You're going to hear a lot today, and I'm really excited about these presentations. A lot of them are going to talk about and offer ideas and thoughts about how we adapt to the future. Bruce and Brick are going to talk about flood warning and the future of hydrology. David's going to talk about new ways to understand risk. And Kristen is going to take us through the history and future of some of our most used tools. And I really am excited for these presentations. But it's not just that. This is something that Laura talked to in her speech, but this is something we all have to do together. It's not something we're going to solve alone. We're going to need new tools, new policies, and new ideas. It's going to have to be all of us. There's a quote that I love from Teddy Roosevelt that goes, "Far and away, the best prize that life has to offer is the chance to work hard at work worth doing." We have new problems ahead of us, and we're not going to be able to solve them without new ideas. But new ideas are hard. Trust me, I've run through enough brick walls. It's hard to do something different. It's hard to risk that it might not work. And it's hard to step forward without knowing where you're going to land. But it's work worth doing. Thank you.